In this video, we will be covering topics related to harmonic analysis while providing an explanation for the inconsistency regarding the definition of poles and zeros and what is observed in practice for a first order system pointed out in the previous video. Further, we would also be focusing on circuits where the output does increase in amplitude or decrease in amplitude as the frequency of the applied input approaches the pole or the zero frequency. Of the numerous ways to characterize circuits, harmonic analysis is carried out by applying an input sinusoid to the circuit under test. In the Laplace domain, harmonic analysis is performed by setting S equal to j omega. That said, let us have a look at the complex plane with the pole location for the passive first order RC low pass filter. As can be seen, the pole for this filter lies on the negative real axis at -1 by RC. The input sine wave, however, has no real parts and lies on the imaginary axis. The transfer function for this filter h of s between input and output, which is 1 over 1 plus s by omega p, has the pole frequency lying on the negative real axis, while the applied input is on the imaginary axis. Setting s equal to j omega in, it can be seen that the transfer function does not cancel out the real part, and hence the output, instead of enhancing, gets scaled down by the square root of 2 at the pole frequency. Hence, it should come as no surprise that the Bode magnitude plot does not show any signs of peak or notch for any first order circuit. Before moving on to the higher order circuits, it is worth mentioning that there are cases in first order circuits in which the output goes to 0 or infinity at the 0 or pole frequency respectively. For instance, the passive high pass and the active low pass filter. In case of the high pass filter, output voltage approaches 0 as the input frequency starts to decrease. On the other hand, the active low pass filter shown here scales up the output voltage as the input frequency moves towards the pole frequency. To explain this, one need only look at their pole or zero location in the complex plane. The pole or zero location for these circuits lie at the origin, which is the common point for both the real and imaginary axis. Hence, at the origin, the frequency of the applied input coincides with the pole or the zero location of these circuits.